All right, general design process. So step 1, choose a radio frequency. This frequency dictates the maximum bandwidth available and depends on the class of the mission. Many CubeSat missions apply for amateur or experimental class frequencies. The spectrum, here's the electromagnetic spectrum, where the radio band is broken out here. And then again, we saw this in an earlier slide, the radio band is then further separated into these smaller segments. And then even if you just look at high frequency HF, that is broken up into even more allocations of frequencies. We are going to do something in the amateur or experimental class frequency that's more on the UHF side. So a question here, will there conceivably be a day when all available frequencies are taken by active satellites? If so, is there a plan for regulatory bodies to control use of illegal frequencies? So the federal law generally prohibits radio broadcasts without a license issued by the FCC. Anyone found operating a radio station without FCC authorization can be subject to a variety of enforcement actions, including seizure of equipment, fines, and other civil and criminal penalties. And the reason for this, the reason why radio frequencies need to be controlled for is because if someone were to transmit a very intense and powerful signal at one of these allocated frequency bands that someone else is trying to use and listen for, then that person is not going to be able to pick up on their signal. You can think of this as, I think there's a term for it called jamming, where you pretty much flood that frequency band with some erroneous signal, with some noise, and that'll prevent everyone else in that frequency band from getting a clean signal, something that's actually desired. That's why we control it. And that's why there are different applications that are associated with frequency bands. And that's why also there are not many, you control the number of people per frequency band. Okay. Next, you choose a modulation scheme and coding algorithm. The coding and modulation scheme determines the required signal to noise ratio and also the data rate. So I should describe what modulation scheme is. Modulation scheme is like that translation of ones and zeros to what that wave actually looks like. There are many different modulation methods that we'll go over later in the week. They can be separated into amplitude modulation, phase, and frequency modulation. And then we've got these continuous phase and trellis-coded modulations. But essentially, a wave has different parameters, amplitude, phase, and frequency, and you can toggle those parameters to get a different stylized wave. Yeah, and we'll go over that later. But essentially, how you modulate your signal is going to affect how clearly you can see your signal. The signal to noise ratio is the how clearly can you see your signal, and the data rate is how much data can you transmit in this signal. And you can see a graph of that effect. So the performance of these different modulation schemes with respect to these modulation schemes. Signal to noise ratio, you want to have a higher signal to noise ratio, right? Because your signal on top in the numerator, noise on the bottom, you want to have much more signal than you want to have noise. So if we look at DPSK, differential phase shift keying, that has a pretty low signal to noise ratio, as opposed to, what is this black triangle? It's QAM. It's quadrature amplitude modulation has the best signal to noise ratio. And then here we have a table of how the different modulation schemes affect your data rate, where the 32 QAM quadrature amplitude modulation gets you the highest data rate, and a GMSK, or Gaussian minimum shift keying, has the lowest data rate. All right, 3, analyze the available contact time the satellite will get using the available ground station's orbit and constellation design if relevant. You'll remember that we did this activity in a previous lecture where we demoed STK with Miguel Nunes. And here from the STK report, you can see the duration of the different ground station passes. So if you combine the data rate with the duration of your ground station passes, then you'll get a total amount of data packet that you'll be able to downlink or uplink, depending on which direction you're going. So this will help you figure out over the span of a mission if you're downloading all the data that you need to finish your mission. Like say for your mission, you want to download 32 megabytes of data, then the data rate and the duration of your ground station passes will give you how long your mission needs to be to fulfill that total data downlink requirement. Okay, next step is to compute the required data rate from all the sources. Here I have some sequence of equations that'll get you the data rate given your modulation bits and your coding rate, which are parameters you'll know. Some roll-off factor. So like, don't so much pay attention to this, just know that there are equations associated with translating data rate with other parameters. Here is a sample calculation for a long-range modulation scheme data rate, where you need to know spreading factor, code rate, bandwidth to get your data rate. So these will be calculated later on in a lab. So don't worry about exactly what the details are now. Then, to finish up, you calculate a link budget and ensure that the link closes with margin. There was a graphical depiction earlier, but many times communication engineers will use these spreadsheets or calculators where you have parameters that you just fill in. You look these numbers up in spec sheets or you calculate them, and then you input them into some predefined calculator, and then it'll get you click to calculate results. It'll show you the it'll calculate the amount of margin you have at the very end in that direction. Here is a sample link calculation from a paper that I grabbed. I'll just show you that these are different types of parameters that you need to know. The spacecraft transmitter power, the spacecraft passive loss that you'll probably have to estimate, the antenna gain, path loss, atmospheric loss, polarization, etc., etc. Those are all things that you'll have to either look up or estimate to eventually get your link margin. The link margin tells you if the link budget closes. Okay. Questions? Does this mean the comm specialist has to be the most flexible out of the subsystems? I wouldn't say that relatively to the other subsystems, the comms specialist has to be the most flexible. I've never been a comms engineer myself, but it's just a different challenge. Yeah, I think every subsystem specialist has different challenges. The challenge with the communications engineer is that there are a lot of variables here that you have to toggle, but it may come with experience and domain knowledge of things that work, like numbers that will work for you to hit a positive link margin. So I wouldn't say that it's particularly harder or you have to be more flexible. It's just a different kind of job.